All right, today we are diving into one of the most ambitious ideas you can possibly imagine. We're talking about the search for a single theory of reality, a kind of source code that could describe everything, from the tiniest particle to the biggest galaxy, all with one single coherent set of rules. So let's get right into it.
But let's kick things off with a question. What if the worlds of physics and biology, which seem so separate, weren't separate at all? What if the chemical reactions happening in your body right now and the light from a star billions of miles away were just different expressions, different dialects, if you will, of the very same universal language?
And that, right there, is the core idea behind something called the Psi-Lambda framework, or Psi-L. It's this incredibly bold attempt to build a single, descriptive language, almost like a fundamental operating system, for absolutely everything that exists.
Now, the goal here is, well, it's monumental. Just imagine for a second being able to describe an atom, a human cell, a star, or an entire galaxy using the exact same set of rules and the same fundamental alphabet. That is the incredible ambition of Psi-Lambda. It's all about finding that universal source code. Okay, so if you're gonna build any language, you have to start with an alphabet, right? You need a set of basic characters you can combine to make words and sentences. So the big question is, what are the fundamental letters in the language of reality? Well, the Psi-Lambda framework proposes that every single object in the universe has what it calls a Psi-Law identity. The best way to think about it is like a unique digital fingerprint. It's basically a standardized chunk of data, a vector, that holds the absolute core properties of that object, whether we're talking about an electron or an entire planet. And what's really wild here is just how simple it is. This whole fingerprint is made up of just 7 parameters. Now, some of these are going to sound familiar, like mass, charge, and spin. Then you've got identifiers for the object and what chemical family it belongs to. The last 2 are really interesting. They're unique calculated properties, something called a logical step, which is related to its complexity, and a signature, which is basically a unique spectral hash. The theory is that these 7 values are all you need to describe anything. Seriously. Okay, so having a grand unified theory is one thing. It's elegant, it's beautiful on paper, but does it actually work? Can it make real, testable predictions about something as famously complex and messy as, life itself? This is the ultimate test. So here's where the rubber meets the road. If this language really is universal, it can't just work for stars and atoms. It also has to be able to decode the incredibly complicated grammar of biochemistry. To put this to the test, the researchers zeroed in on a very specific, well-understood area: how vitamins and minerals interact inside the human body. So here's how they set up the experiment. It's pretty clever. They took 100 different pairs of vitamins and minerals, and for every single pair, they used the Psi-Lambda framework to calculate a theoretical affinity score, basically a number that predicts how strongly those two things should interact. Then, they just compared that score to what we already know from decades of real-world biological research. First up, they looked at synergies. These are the dynamic duos of nutrition, the pairs of nutrients that help each other out, making them easier to absorb or working together on some biological task. Now, if the framework is correct, these pairs should have a really high affinity score. And the results? Well, they're a fantastic confirmation. We all know vitamin C helps you absorb iron, right? Psi-Lambda predicts a high affinity. We know vitamin D is critical for calcium absorption. Boom, Psi-Lambda gives it a high score. And vitamin B12 literally contains a cobalt atom. They are fundamentally linked. Psi-Lambda calculates a very high affinity score. As you can see, it's a perfect match every time. Okay, that's pretty cool. But what about the opposite? Can the language also predict conflict? I'm talking about antagonisms, nutrients that actually compete with each other in the body. According to the Psi-Lambda language, these pairs should have a low affinity score. Let's see if the theory holds up here, too. And yep, once again, the results are remarkable. Zinc and copper are famous for competing with each other in the body. The framework predicts a low affinity score of 0.40. It's a match. We know that too much calcium can block iron absorption. Psi-Lambda calculates a low score of 0.45. Another match. And the toxic metal cadmium is known to mess with zinc's function, and you guessed it, another low score of 0.40. The framework is correctly flagging these negative interactions. So here's the real punchline. This wasn't just about a few cherry-picked examples. Across the entire validation study, all 100 of those nutrient pairs, including synergies, antagonisms, and neutral pairs,
The predictions from the Psi-Lambda framework showed over 95% coherence with established biological reality. It was essentially reading the logic of nutrition from first principles. That's just incredible.
This biological test is astounding, for sure. But remember, the whole goal was a universal language. So does the exact same logic, the same math, hold up when we zoom out from our bodies to the scale of the entire cosmos? Let's start small, with a single hydrogen atom. Using its rules, the Psi-Lambda framework predicts that this atom should emit light at a very specific wavelength, 121.55 nanometers. So what do astronomers actually see when they look out at the universe? They see 121.6 nanometers. That's a tiny, tiny difference of 0.04%. The prediction is totally coherent with what we observe. Okay, now let's go big. Let's go all the way back to the beginning of time itself, the cosmic microwave background. It's the afterglow of the Big Bang. The Psi-Lambda framework predicts its peak frequency should be right at 160 gigahertz. And what do our most advanced satellites, like the Planck telescope, actually measure? Exactly 160 gigahertz. It's another perfect match. And for one final test, let's look at those huge clouds of gas floating between the stars in a galaxy. Psi-Lambda calculates that neutral hydrogen gas should give off a faint radio signal at a wavelength of 21.0 centimeters. And this is one of the most fundamental measurements in all of radio astronomy. What do we observe everywhere we look in the universe? The 21-centimeter line. It's coherent across all scales. It just works. So, what does all of this actually mean? We've got a single framework that can predict nutritional chemistry in our bodies and the light from ancient galaxies, and it does it with stunning accuracy. This is pointing towards something incredibly profound about the nature of reality. One of the source documents just nails the essence of this, stating, "C'est un langage émergent." It is an emergent language. And that right there is the key insight. The rules of biology weren't programmed into this model. They just emerged from the fundamental physics. The grammar of life just appeared on its own, simply by applying this universal alphabet. This forces a massive shift in how we look at this. The big takeaway here isn't that we've just invented some clever new model. It's that we might be taking our very first baby steps in reading a language that was already there all along, written into the very fabric of reality itself. And that, of course, leaves us with one final, kind of awe-inspiring question. For all of human history, we've been trying to understand the rules of the universe. But if we're finally starting to actually read its source code, well, the next logical step isn't just to understand it. It's to build with it. So what will we write next?